Ready to level up your physics game? From Pythagoras to vector angles, let's crack the dot product's secret code and transform abstract math into useful geometric insights. So in today's video, we have a 2-for-1, problems 1.3 and 1.4. In 1.3, we have, by applying Pythagoras' theorem, the usual two-dimensional version, twice over, prove that the length r of a three-dimensional vector r equals x, y, z, so we're just somewhere in space, satisfies r squared equals x squared plus y squared plus z squared. And in 1.4, one of the many uses of the scalar product is to find the angle between two given vectors. Find the angle between the vectors b equals 1, 2, 4 and c equals 4, 2, 1 by evaluating their scalar product. So let's kick things off with problem 1.3. Picture this. You're in a three-dimensional coordinate system and you need to find the length of a vector. How do you do it? Well, we're about to see how our old friend Pythagoras comes to the rescue, not once, but twice. First, let's consider the xy plane, where we see a triangle made from blue, green, and red. Okay, by applying the Pythagorean theorem here, we get L squared equals x squared plus y squared. But we're in 3D, so we're not done yet. And this is the second application of the theorem. Now we treat L as one side in this triangle here, C as the other, and this R is now the new hypotenuse. So by applying Pythagoras' theorem again, we see that we get R squared equals L squared plus Z squared, but this L squared we found from the two-dimensional version up here was x squared plus y squared. So therefore, we see that R squared is equal to x squared plus y squared plus Z squared. And there we have it. We showed that the length of R of a three-dimensional vector that we see here satisfies the equation given. Okay, now to actually see the length, we have to take this square off by taking the square root of both sides, but that's pretty easy, all things considered. Now, what this elegant result shows is how two-dimensional concepts extend beautifully to three dimensions. And if you're a mathematician, we can concoct other dimensions higher than 3. So be aware, there's a lot more to this landscape of vector algebra than we give credit to in physics. And if you're finding this video breakdown helpful, give this video a thumbs up and share it with someone who might benefit from it. Moving on to 1.4, where things get a little more interesting. Here we're given two vectors, b and c, as we see in unit vector form and angle bracket notation form. Now, our mission is to find the angle between them. This is where the dot product shines. Remember, the dot or scalar product mathematically links vector orientation by revealing the cosine of the angle between them. And this is the geometric definition mentioned last video. So what we see here is that the dot product b dot c is equal to bc cosine theta, which is equal to the magnitude b and c times cosine. So I had to do this because it's a little notational thing that we have to keep track of. When you see a boldface letter here, in this book that indicates a vector, but a non-boldface italics is considered just a length or magnitude. But in the vector landscape, to get rid of that ambiguity of notation, we just put the vector inside these vertical bars to indicate the magnitude. And now from here, we can solve for cosine by dividing the magnitudes over and then taking the inverse cosine or the arc cosine on both sides to highlight the angle here. And from here, we see that we have b dot c up top, but what is this b dot c and what are these magnitudes that we speak of? So from equations 1.7 and 1.8, we can put this theta form into the full component form. So equation 1.6 gives us the geometric definition of the dot product, which looks like a scalar or projection of one vector onto the other. So think about a shadow. And in the shadow, we can determine how much it overlaps tells us what angle it's at based on the size of the vectors. So that makes sense in a kind of geometric trigonomic relationship perspective. Whereas in 1.7, we have the algebraic definition, which we used last time. And this is all the component forms, and we'll have to use this one again in the numerator of the theta equation. Now, as far as the magnitudes go, we just showed in 1.3 that r is equal to x squared plus y squared plus z squared. Generalizing that to any number of coordinates, taking the square root, we see that this is actually the length that we found last question. But we could generalize this to the vector notation where we have the bold vector in the vertical bars, which is actually equal to the dot product of the vector with itself in the square root. So pretty nice self-consistency there. So putting these in there, we see that we have theta equals arc cosine of the algebraic dot product up top and the magnitude of b and c respectively. So now that we have this theta in terms of a full vector component form, we can just plug in from our vectors. So we have 1, 2, 4 from B, and then we have 4, 2, 1 from C, plug them in. We have 1, 2, 4 from B, 4, 2, 1 from C, square them, multiply them out, and we see that the numerator gives us 4 plus 4 plus 4. The denominator gives us 1 plus 4 plus 16. So both of those sum to 21. The numerator sums to 12. And since we have two square roots of the same value, that's 12 over 21, which gives us an approximate angle of 55.15 degrees. Again, be careful in your calculators to make sure you're in degree mode or radian mode. Whatever the number is, just be aware what mode you're in so you can report it back accordingly. And so we found the exact angle between our vectors using nothing but the geometric and algebraic forms of the dot product and some basic tricks, so it's really not too bad. Now, these problems showcase the power and elegance of vector mathematics and physics, something we will use over and over again. The dot product isn't just a mathematical trick, it's a fundamental tool which allows us to understand the geometric relationships between vectors in any number of dimensions. And we'll see that this dot product definition comes again when we try to check on things like orthogonalities of vectors. Very important for us. But remember, mastering these concepts is key to excelling in classical mechanics and physics in general. So keep practicing, and soon you'll be seeing vectors and dot products in your sleep. So if you're passionate about understanding classical mechanics, hit that subscribe button so you don't miss my next video in this series. Huge thanks to my Patreon supporters. Your backing enables me to create in-depth physics content. Your support truly drives this channel forward. If you want to support our physics exploration, check out the Patreon link in the description and join our scientific journey. As always, thank you for watching, and until next time, stay curious.